All right, in this video, we're going to be talking about the Impulse-Momentum Change Theorem. So, tying in Newton's second law. So remember, Newton's second law says that F net equals m times a. It states that the acceleration of an object is directly proportional to the net force that's acting on the object and inversely proportional to the mass. And all that's saying is that if you increase the mass of something, you're going to have to increase the amount of force that you're using to accelerate it. If you increase the mass, but you don't change that force, it's going to decrease the acceleration. So we've already looked at Newton's second law. You should be very familiar with it. So we've been talking about momentum and objects in motion, right? Momentum is mass in motion. Any object with momentum is going to be hard to stop. It's going to take a lot of force, right? To stop such an object, it's necessary to apply a force against its motion for a given period of time. You already know that if an object's moving to the right, you're going to have to apply that force in the opposite direction, so the left, in order to get it to move. And it may not just be a 1 second force. Maybe it takes 10 seconds of applying that force. Maybe it takes 2 minutes of applying that force. So you have to apply that force against the motion, and it is for a given amount of time. And of course, the more momentum that an object has, the harder that it is to stop. More momentum meaning a huge 18-wheeler driving down the road. To try to get that 18-wheeler to stop, it's going to require a lot of force and a lot of time. But maybe a little bike or a smart car, that's very little momentum. So you wouldn't have to apply quite as much force, and maybe it wouldn't even take as much time either. So thus, it would require a greater amount of force or a longer amount of time, or sometimes both, to bring an object to a halt or a stop. As the force acts upon the object for a given amount of time, the momentum is changed. So you would end up having an initial momentum and a final momentum, because also the velocity is changed. So impulse is actually the change in momentum. So remember, we like to represent change with the delta symbol. So the delta of P, the delta of momentum. So the change in momentum. So change, that delta triangle sign. And then remember, momentum is P. So the change in momentum is because velocity is changing. So the velocity is changing. That means we also have an initial and a final velocity. So remember, momentum is mass times velocity, right? But if we have an initial and a final, that means that there's a change in this velocity as well. So really, the momentum is calculated by mass, and then you're going to multiply the final velocity minus the initial velocity. Because remember, we always do final minus initial. Okay, so on to more definitions and equations, right? Impulse. Impulse is not represented by the letter I. It's going to be represented by the letter J. So when we're solving for impulse, it's actually going to be a J to represent it. So impulse measures the change in momentum. So the amount of momentum change happening before a collision to after a collision, to an object just starting off to an object stopping. The equation for impulse, remember, J is impulse, is equal to the change in momentum. So again, that change, that delta symbol, in momentum, P. So that's equal to the final momentum. So PF is the final momentum minus the initial momentum, PI. You could also see that the change in momentum, so delta P, is equal to the mass times the change in velocity. Because remember, velocity is changing. The mass isn't changing. The object's mass is remaining the same for 99% of these scenarios. But the velocity is what's changing, because we're changing the movement, the motion of the object. So remember, change in velocity can be broken down into this. So final velocity minus initial velocity. All right. So to calculate impulse, you could also do it a different way. So impulse can actually be calculated by multiplying the average force that's acting on the body by the length of time that the force is acting on it. So that means that you would solve impulse, J, is equal to F, which is the force, and remember force is always measured in newtons, represented by N, times the length of time. So time, and time is in seconds. And it is a change in time because we're starting from usually time 0 to time 5 seconds, time 0 to time 15 seconds. Okay, so because it is actually impulse equals force times time, the units for impulse would be Newton, because a force is represented by a Newton, times, because we're multiplying by time, seconds. So impulse is equal to newtons times seconds. And again, we have this huge long formula. I know it looks overwhelming, but I promise it's not. This formula just means that you could solve impulse by the change in momentum. And the change in momentum is equal to mass times the change in velocity. Or impulse is also equal to force times time. Okay, so how did these equations even merge together like this? So we actually took Newton's second law and we just manipulated it a little bit. So Newton's second law says force equals mass times acceleration. All right, and we also know that acceleration can be written in this format. So acceleration is the change in velocity over time. So that means we could plug in the change in velocity divided by time in place of A. So that's actually what we did. So in place of A, we plugged in the change in velocity over time. So that gave us force equals mass times the change in velocity, all divided by time. And then, just to make it, make us do a little bit more work, we can actually get rid of our dividing time and move time to the left-hand side. So, of course, we would multiply by time, the time cancels out on the right-hand side, and that's how we ended up with our equation looking like this. So force times time, or time times force, same thing, is equal to mass times the change in velocity. And the change in velocity is the final velocity minus the initial velocity. Okay, notice impulse is on the left side. So this is our equation for impulse, is equal to the change in momentum of the object. This is how you solve for the change in momentum, because momentum is mass times velocity. Okay, Impulse-Momentum Change Theorem. So in a collision, an object experiences a force for a given amount of time that results in its mass undergoing a change in velocity. That results in a momentum change. So impulse is force times time. The change in momentum is mass times the change in velocity. And then you just set them equal to each other. So if the last slide didn't make sense, just know that impulse is the change in momentum. To find impulse, we have force times time. And to find the change in momentum, we have mass times the change in velocity. And all we do is just set them equal to each other, because impulse and the change in momentum are the same thing. We're saying the same thing here. Okay, so speaking of collisions, when we talk about collisions, it's when two objects come in contact with each other. And there are several different types of collisions that we're going to look at. So in case A, you can see that the car at first, it's going towards the wall, right? It hits the wall and then it bounces off the wall and moves away. Notice how the velocities are different, right? It's moving 5 meters per second into the wall. After it hits the wall, it loses a little bit of velocity. It's only moving 4 meters per second. On the other hand, case B, you have this car moving same speed, 5 meters per second into the wall, but in case B, it actually gets stuck to the wall. So its final velocity is 0. The car does not bounce off the wall. So we're actually going to be focusing on the effect of collision time. So how long does this collision actually take? Is it 2 seconds? Is it 5 seconds? Is it half a second? And then we're also going to be looking at the effect of rebounding, or how it interacts with each other. So does the velocity change? In case A, it did. Case B, it did as well. So, just to show you more for impulse, remember impulse is the change in momentum, and we can also find it by the force times the time. So, in this scenario with this table, okay, so our impulse is 100. Notice how on our table, the impulses for every scenario is 100 because it says that the object has 100 units of momentum. So it must experience 100 units of impulse in order to be stopped. So that stop, you could change the amount of force for the stop, or you can change the amount of time for the stop. So impulse always has to be 100, right? So there's several different scenarios. You could apply 100 newtons of force. It would only take 1 second. There's your 100 units for impulse. You could apply less force. Maybe you only want to apply 50 newtons of force, but it would take twice as much time, 2 seconds. Maybe you have even less force to be able to apply. Maybe the force is only 25 newtons, so it would take 4 seconds to stop whatever moving object it is. Maybe you only have 1 newton of force, so that means it's going to take 100 seconds. So as you decrease the force, you lessen the amount of force that you want to apply. Notice how it takes way more time. So as you increase the force, the time decreases, and vice versa. They are inversely related proportions. So applying this impulse-momentum change theorem. So in short, we have momentums. We have airbags in our cars, right? So airbags help to minimize the effect of force on an object, because airbags extend the time required to stop the momentum of the driver and passenger. We've already talked about how whenever we're driving down the road, our bodies have inertia, right? Because whenever we start slamming on the brakes, our seatbelts lock because our bodies keep moving forward. Well, in a crash, that airbag helps to extend the time. It acts as a big cushion to extend the time that our bodies are moving forward into the windshield. So instead of hitting the windshield, the driver and passenger hit the airbag, then the time duration of the impact is increased. So you're taking, maybe it's 30 seconds to move into the windshield instead of 1 second. So when hitting an object with some give, such as an airbag, the time duration might be increased by a factor of 100. Increasing the time factor by a factor of 100 will result in a decrease in the force by a factor of 100. So, 100 newtons less of force applied to your face if you can increase the time by 100 seconds. Crumple zones of the car. So even if you get in a little fender bender, your car crumples up at the back or at the front, that's on purpose. It's not because your car is built in a cheap way. That is so that your car can absorb some of that force applied and increase the amount of time. So increase the amount of time, decrease the amount of force applied to your body.